Hello, everybody. This is Deborah Elmore from the Bay Area Association of Kidney Patients. Thank you for joining us this afternoon. We have a very exciting program with great speakers. It's New Frontiers in Kidney Transplant. And just a few housekeeping things. If you have questions, you can put them in the Q&A and the speakers will be able to see them. You can't raise your hand in this and we can't see you. So put them in the Q&A and the questions will be answered at the end. And I really want to thank Ward, our program manager, for putting together this webinar for us. So with that, Ward, I'll let you take over.
Okay, thanks, Deborah. We're going to have a three-part program here. Dr. Jeffrey Stern of NYU Langone Transplant Center in New York City is going to talk about the surgical aspect of xenotransplantation. And Vasishta Tatapudi, who he works with as a transplant nephrologist, is then going to talk about the medical, technical, and pharmaceutical issues with xenotransplantation. And then Shuvo Roy of UCSF is also with us. He's going to talk about the artificial kidney project, of which he is the technical director. So we're going to start with Jeff, who earned his MD at New York Medical College. He's, as I said, a transplant surgeon at NYU Langone. He specializes in kidneys. And he's an assistant professor of surgery at the Grossman School of Medicine across the street from Langone. And as a member of the Langone team that has done 2 of the 4 xenotransplants to date, both of those in 2024, using pig kidneys. And I want to say, as a side note, he's a special person to me. I first met him over the phone 13 months ago to this day, when he called to say that he had a kidney for me. If I could get to Langone by 9 a.m. the next morning. So I rushed to the airport, got the last seat on the first red eye, got to the hospital at 7:30 on the 28th, and had my kidney implanted or transplanted that day. So I recently celebrated the 1-year anniversary of the beginning of a new life. And thank you, Dr. Stern. You now have the floor, or should I say the camera.
Sorry, was still muted. Well, much appreciated, Ward, and yeah, those were certainly a special day for both of us. All right, I think, can you guys see my screen okay?
Yes.
Amazing. All right, so I will run us through sort of what we've done with xenotransplantation so far at NYU and go through sort of why we're even researching the field of xenotransplantation and hopefully some of the prospects and the hopes for the future as we go through. I always think that it's important to know sort of the backstory of anyone giving you information, and so I try to overshare in disclosures for the most part. And in that, a lot of our funding is provided by several companies that are making a lot of the pigs, and so I think that's important because they obviously have incentives to get this product out to everyone. There's a dual purpose, though, right? In that they create the pigs and they have funded a lot of the research behind it in the hopes that one day, this will become an everyday practice. We like xenotransplantation because I think it provides patients a lot of hope for the future, given the current organ shortage. And I'll go through that in quite a bit of depth in the coming slides. I also I implant kidneys and I take out kidneys from living donors, but I also procure livers for our liver team, and sometimes I do that for Transmedics as well. And if it's post lunchtime, so hopefully it's okay, but I will be showing some anatomic pictures. Of course, I work at NYU, and so I'm definitely focused on the things that we have done at NYU, but the field of xenotransplantation is quite small, and so often we know a lot of the things about the other institutions and what they've done. But I'll talk predominantly about kidney, and I'll talk predominantly about the NYU experience since I know most about it. But overall, want to give sort of my overview of the field of transplantation and how we've made progress over time and why we are where we are with xenotransplantation currently. We'll go through some of the current options, what we can do about some of those things, and you'll hear some about that in the later talks as well. And then I'll talk a little bit about who may be the best candidate, and then where we're going to go from there. So I like to look at, transplantation in general into sort of 30-year time periods. The first 30 years from the first identical twin transplant in 1954 with Joseph Murray in Boston, where there was no immunosuppression needed for the technical aspect of the transplant procedure to be successful. Also, notably, the first living donor to be able to donate and survive afterwards. That first 30 years was marked by progressive increases in technology and pharmaceuticals to allow appropriate immunosuppression to have kidney transplantation be an everyday process. And until tacrolimus came onto the field, that was a very it was rare to have long-term allograft survival. The second 30 years is really when transplantation hit its stride and became an everyday process. We now expect 1 year allograft survival to be upwards of 90% and patient survival to be even higher than that. And that's all because of the immunosuppression medications. We really haven't had a lot of new immunosuppression medications in the last decade. The best one, or the most recent one, is belatacept, which came out after 2010. And that has really been successful at allowing organs to heal from a marginal state. And that really allows us to implement tacrolimus as a delayed therapy rather than an early therapy. And that really is sort of where we are today. I hope that we're on the precipice of the next 30 years, the third 30 years, as xenotransplantation comes into its stride, and we hopefully will make progressive advancement and increases in its utilization. So currently, the only options for patients with end-stage renal disease or chronic kidney disease, which is an impediment to life, is a living donor transplantation, direct donation from a donor to a recipient, or what has become increasingly prevalent is paired exchange, which is sort of disjointed pairs, or everyone sort of getting the best of both worlds, which is really, I think, a fascinating part of modern living donation, is where it's a win-win situation. There are very few win-wins in the world, but if someone can donate a kidney or is willing to donate a kidney to you, but instead of donating to you, they donate to someone else on your behalf, and you get a voucher to get a better kidney for yourself, and the person that's receiving the kidney from your donor also gets a better kidney because each of those pairs was a better match. It's very rare to have a win-win situation in anything in the world, but living donation and paired exchange is certainly one of those scenarios. So that's becoming more and more prevalent as we talk about eplets and better immunologic matching between donors and recipients. Unfortunately, not everyone has a living donor. And that's where we look at the organ supply and we look at the deceased donor waiting list. We can use single kidneys. We can even use kidneys that aren't good enough to be used as a single kidney and transplant both of those kidneys as dual kidney transplantation. But those are really the only options. The number of patients on the waiting list continues to increase, as you can see in the left-hand graph here. And the number of people on the waiting list continues to increase, and the number of kidney transplants being performed also continues to increase, as you can see on the right-hand graph. The number of donors, so deceased donors is what we're graphing here, also continues to increase year over year. With some reporting around COVID and other things, the incidence, so how many people develop end-stage renal disease, has progressively increased up till about the year 2000, and it started to go down a little bit. But again, I think that's more of a reporting issue or stabilization of how many patients we can sort of maintain with end-stage renal disease nationally. So as I mentioned, all of the deceased donors that are recovered in the United States has continued to increase year over year. A number of living donors has remained quite stagnant, right around 5,000 living donors per year. What do deceased donors die of? And this is really sort of an interesting and story of the opioid epidemic. So I think you guys should be able to see my cursor as well. But the number of donors who had stroke or had an intracranial hemorrhage or became brain dead and were able to donate after brain death has remained roughly stable. What has increased are the cardiovascular donors. We're getting a little bit better at restarting hearts. Unfortunately, in that process, a lot of those patients are becoming brain dead and they're increasing part of the donor pool here. The other thing that's increased dramatically since 2010 are the number of donors who died of a drug intoxication. And so I'll point your attention to the right-hand graph here first, and this is the number of deaths involving heroin. And you can see that there was a peak, and as the heroin epidemic was addressed, the number of deaths from strictly heroin overdose has decreased dramatically, and heroin plus another opiate has also started to decrease. And so you can see the slope and the curve of those lines. If you look at all overdose deaths, not opioid-specific ones, you can see that that curve is starting to level out. And it's not just because of the heroin overdoses decreasing, but our expectation is that overdose deaths will decrease over the coming years. And that means that a lot of very viable organs for transplantation will not exist from that donor pool. And so that our total number of donors may stagnate and become stable and or decrease. So there aren't enough organs. So what happens afterwards? How do we increase the donor pool without decreasing the number of transplants? Obviously, more and more people are needing it, so we can't just stop transplanting people. Can we use more marginal organs? Should our expectation of how our 1-year allograft survival is be changed? Should we say it's okay to get someone off dialysis for less than a year, but get them transplanted? And maybe that's part of the answer. And maybe as new immunosuppression medications come around, we'll do better at maintaining marginal organs for a longer period of time. A lot of other body systems besides for kidneys have started to put hearts on ex vivo normothermic pumps. So they're pumping blood and reviving hearts that wouldn't have otherwise been able to be utilized. And they're seeing how they're doing before they put them in. Same thing for lungs, livers. Problem is, and there's actually one group that did get an ARPA grant to do normothermic perfusion of kidneys, just not commonplace yet. It's not FDA approved as of yet for common practice. So can we also increase the donation rates, right? So if an increased number of living donors happen, we could increase our number of transplants. And if more people register to become deceased organ donors, it may be able to increase our deceased donor utilization. But again, how people die isn't really changing. So can we recellularize organs? Can we take donor cells off of the scaffold that the organs have and recellularize them? Maybe. The artificial kidney you'll hear about later on today. And then really the thing that piqued everyone's interest is, can we use a non-human organ for our donor supply? And that's really where the idea of xenotransplantation came about. This are just some examples and brief videos of hearts on pumps. Lungs on pumps is on the top left, top center is heart on a pump, and then the liver doesn't look as sort of mobile in the middle. And on the bottom is actually the LifePort kidney transplanter, which is a cold or a hypothermic, you can see the ice over here, machine pump. Pumping organs, revitalizing organs is nothing new. People have been doing it for a long, long time. Alexis Carrel and Charles Lindbergh actually experimented with that and published in 1935. And this is, I think they put chicken hearts on these pumps in the bottom right. So what is xenotransplantation? Xenotransplantation is the transfer of cells, tissues, or organs from non-human sources into humans, or between species, essentially. For our purposes here, we'll talk about it from other animal sources into humans. But anytime you cross the species barrier, that's called xenotransplantation. And for a long time, we've looked at pigs. There are some xenotransplants that have happened, baby Faye being one of the most notable of those, which was a baboon heart transplanted into a very young child and lasted a couple weeks. But there was a lot of concern at the time that there could be transmission of virus from very close relatives of humans, and when you transplant and cross circulate those species. And a lot of the moratoriums, or the moratorium on doing that, was right around the HIV and AIDS epidemic, when we were unsure of sort of what the mechanism of that was and how viruses were transmitted between species. And so pigs are far enough away from humans that the zoonotic risk, the risk of transmission of a virus from a pig to a human, is thought to be very low, that even if something was transmitted, it would probably be isolated to the organ itself. But a lot of that remains unknown. But a lot of the receptors between pigs and humans are quite different. So the risk of infection is thought to be quite low between pigs and humans. Pigs can be bred to be pretty much the size of humans. Miniature pigs really equate to the size of humans, and you can knock out the growth hormone receptor in pigs to make them their final size about the size of an adult human. Anatomically, they are quite similar, and I'll leave it to Dr. Tatapudi to talk about some of the major physiologic and chemical similarities and differences in some of the things that we've tested along the way. And the other thing is that pigs can have a large litter, and so you can really think about ending the organ sort of demand issue with an increased supply, with lots of pigs with lots of litters. The other thing is that for lots of different reasons, most humans, not all humans, eat pigs, and it is really a regular source of food across the planet. There's even metrics and quarterly hog and pig inventories graphed out over the most recent years on that there are always around 75 million pigs alive at any one time, and lots of those are slaughtered for food and the bacon for your breakfast sandwich in the morning. The thought is about 1.5 billion pigs are used for food or other purposes per year. And so the thought is that pigs could really be that supply of unlimited organs for us. The problem, and the reason why we haven't done it so fast, is about 40 years of xenotransplant research that triggered a realization that there's a sugar, which is this alpha-gal moiety that you see on the left, and this is just a graphic representation of that humans make very strong antibodies against gal. And part of that is because a lot of bacteria express gal, and our way of defending ourselves is to create a lot of antibodies against it. And when you transplant organs from pigs to humans that maintain the alpha-gal expression, there's what's called hyperacute rejection. The kidney almost immediately turns blue, and the blood clots in the kidney, and it's non-viable. In around the early 2000s, 2002, I believe, using certain technologies, we were able to, not we, but the group in the field was able to knock this sugar out. They were able to knock it out of the genetic sequence of the pig cells and to allow it to no longer express this sugar at the top of its glycoproteins. And that way, the organ is invisible to those antibodies, and you don't get hyperacute rejection. Hyperacute rejection is what you see at the left-hand side here. And on the right-hand side is actually our first pig to brain-dead human transplant. And this is right in the groin, the femoral vessels are where we connected this kidney to. And this is back in 2021. And this was a new model that had never been used before we did it at NYU. And Dr. Montgomery sort of spent many years developing both the ethical and the practical framework behind this. But essentially, organ donors that are brain dead, that don't have organs that are suitable for transplantation for various reasons, either because of age or chronic kidney disease, end-stage renal disease, heart failure, various other scenarios that make none of the organs transplantable. We were able to access that donor supply and consent the families to perform xenotransplant research at that time. And so this kidney we implanted in the femoral vessels, and we watched it for about 54 hours, and we didn't see any hyperacute rejection. The kidney remained pink, made tons of urine, and that was really the sort of first step. And xenotransplantation made large sort of media presences right at that time, that it was very exciting that the thing that we thought wouldn't happen didn't happen, and really allowed us to progress with a lot of the other things that we've been doing now. After those first very short-term studies, we did a long-term xenotransplant. We had a decedent, someone who was brain dead, and we took out both of their normal kidneys, and we implanted a xeno kidney into their the normal place where you put a kidney transplant. About 5 months prior to doing that, the thymus, which is an organ that helps us generate our T cells. Our T cells provide the cellular-based immunity for our immune systems, to allow it to educate, to both revascularize under the kidney capsule. And the thought was that when that cross-circulated, we could educate humans' T cells in the pig thymus to allow human T cells to think that pig was self, at least from a cellular perspective. And we have some early data to say that we think that that is starting to happen, although we don't have 100% conclusive evidence of that just yet, but there's more work to come there. So after we did the transplant into a brain dead decedent, we watched that patient or that donor for about 2 months. And the whole time they made urine. And I'll show you some graphs of how their creatinine and renal function did after that. What you see on the right-hand side of your screen here, the bright blue is actually the thymus, and normal kidney tissue is even further to the right here. And that shows that the thymus was successfully implanted and the structure was maintained underneath the kidney capsule. And so this is sort of a smoothed out graph of what we're showing, but the black line here coming down is the serum creatinine, which came down and stayed quite low for the first month. We did have an episode where the creatinine began to rise, actually 2 times. I'll go into that a little bit more. But essentially, the decedent never needed dialysis, and we were able to treat all the things that came along the way. Another term that a lot of people use is glomerular filtration rate, or creatinine clearance. And that's a little bit easier to understand. As the number goes up, the function is increased, and as it slopes down, the function of the kidney is decreased. And so just after a month, the function went down. We were able to perform a biopsy, show that there were some early signs of antibody-mediated rejection. We were able to do a process called plasmapheresis. And plasmapheresis is exchanging the plasma compartment of your blood. It's similar to dialysis. You take blood out of a human in small segments, and you wash essentially what's between the cells in the blood, and we're able to wash antibodies essentially from blood using that process. And we did that a couple times, and we were able to see the function improve, and we repeated the biopsy, which showed incomplete resolution of our rejection. We treated again with some other medications, including thymoglobulin, and more plasmapheresis, and we were able to fully resolve all the features of rejection by the end of the study, which is really both the first time that we were able to actually treat xenograft rejection. It's the first time it's ever been treated in primates, any of the primate studies, or any humans to date at the time that we did this. For those of you that are histologists or know what a normal glomerulus looks like, this is a pretty normal glomerulus on the left-hand side here, and the podocytes. This is an electron microscopy image, which these are sort of the filtering units of the kidney, and we look at these bridges between them, and all of those, what are called foot processes, were intact. So the kidney looked great after about 2 months implanted. This is a large image when we went in to end the study. This is a very normal looking and really beautiful looking kidney after that time frame implanted. So I'll go into a little bit more detail on our second living recipient. Our first one was, for lots of different reasons, and we don't quite have time to go into it, a really sort of heroic effort at someone who had heart failure and end-stage renal disease, and trying to get her more time. Our second recipient, though, was quite unique and ended up receiving a 10 genetically edited pig kidney with the growth hormone receptor knocked out. But She was in her 50s. She had end-stage renal disease. She had actually a prior donor. Her mother was also in need of a transplant. And unfortunately, after she donated, she became pregnant, had preeclampsia, and had several sort of episodes that led to her worsening renal function. Eventually, she needed to go on dialysis. Unfortunately, she had what's called a CPRA, or a panel reactive antibody level of 99.999%, pretty much as many as the nines go is what she had. She was very sensitized to other humans. So panel reactive antibody is what I like to describe it as is, if you look at your antibodies and you look at 100 people in the room, if you have antibodies against any particular person that you couldn't receive a transplant from them, that would increase your number by a certain percent. So if you had antibodies against just one of those 100 people, your PRA would be 1. And if you have antibodies against all 100 of those people, it would be 100. And you can't actually have antibodies against 100 because you still exist, and you can't, or you shouldn't, develop antibodies against yourself. And so that number can never theoretically be 100, but it can certainly round up to 100. So she had antibodies against almost everyone that could have been a donor for her. And she, for all intents and purposes, had no acceptable kidney offers in all the time that she was on the waiting list. She also had extra priority on the waiting list because she was a prior donor. And so the FDA was petitioned to do what's called a single patient investigational use of this 10 genetically edited kidney, and we transplanted her in November. And this is just a brief graph of her function and her course. The kidney lasted for about 130 days. She did have an early episode of rejection, but her kidney function stabilized. She made great urine throughout the course. She was discharged. She lived a very active life as far outside of the hospital as she could be for as long as she could be over this program, certainly with very frequent check-ins. And eventually she unfortunately suffered a pretty severe rejection episode in response to a lowering of her immunosuppression because she unfortunately had a couple infections, and we lowered her immunosuppression. And then unfortunately she had a rejection, and we had to take out her kidney. But she was a great example and a great patient. As one of our first trials, she was by all intents and purposes a great success early on. And unfortunately she lost the kidney due to a rejection, but we learned a lot, and she's back on dialysis unfortunately at this point, but doing okay otherwise. There are early and first approvals of clinical trials which really should be starting imminently. I think we'll hopefully hear about those happening very soon. Multiple companies are submitting both series and cases and sort of full clinical trial proposals to the FDA, and Dr. Tatapudi will probably chime in on that a little bit more. But yeah, there's lots of progress being made in the field around that. But who at the moment would benefit the most from a xenotransplant? And really the short answer is we don't totally know who would benefit the most from a xenokidney right now. A lot of the long answer to that is that anyone who's not likely to get a transplant currently on the waiting list or die or become too sick while they're waiting for a human organ would probably benefit from a xenotransplant. Essentially, any time that you're off dialysis, whether it be 6 months, a year, 2 years, is generally considered beneficial in the course of one's life. And so the longer we can keep you off dialysis, or the amount of time that we can take you off dialysis, there's probably some benefit overall. Obviously, there's risk of immunosuppression, the transplant procedure itself, but there are some patients who are losing dialysis access and don't even have the option to stay on dialysis. And so those are obviously some of the early targets for these clinical trials and for some of the investigational uses. And especially those patients who are highly sensitized, have antibodies against lots of other humans, they're very underserved just because the donor pool of human organs is so small. And what we've shown in a lot of our studying up to this point is that the the antibodies that humans generate against other humans don't tend to cross-react against the antibodies that you would generate against a pig. And so that really does benefit xenotransplantation for those patients as well. The other thing is, how do we define success? The first human-to-human heart transplant lasted something like 18 days. The first pig heart to human lasted about 6 or 8 weeks. So we were more successful now than we were before, but how do we define success along the way? I won't go through all of these just for the sake of time, but there have been several pig to human transplants, and there's even another one that's not listed on here. But we're making progress with each iteration of pig to human transplantation along the way. We don't currently know how much it's going to cost. Ideally, it would be similar to what a living donor or a cadaveric human organ would cost. Some of the immunosuppression medications that we need to use right now are more costly. We use them in allotransplantation, but in xenotransplantation, they're more off-label, and it's hard to get those approved by insurance, but certainly that's on the threshold of lots of things we do. Hopefully, the process of implanting or auto-implanting the thymus may be beneficial in the long term at reducing the need for long-term immunosuppression. Maybe one day we'll be able to modify the pig organ enough that we don't need any immunosuppression or very low immunosuppression to perform these transplants. How much are the pig kidneys going to cost? Not sure. We don't know that yet. Early trials and advancements, and ultimately, there should hopefully be an inflection point between the time that these organs last, how much they cost, and how often you need to replace them. Clinical trials are starting very soon. Hopefully, at some point in the next 2, 5, maybe 10 years, xenotransplantation is my hope would become common practice for the things that we're doing. Obviously, all the data above is a collection of a huge team at NYU. Dr. Tatapudi, one of those main people for us as well. But certainly I couldn't talk about any of these things without the breadth of people behind us. So thank you.
Thanks so much, Jeff. I thought I would just mention, you mentioned Dr. Montgomery. He is the director of the NYU Transplant Institute, or the center, and is himself a heart transplant recipient for a number of years. So he really understands what's going on. It has a personal interest in making these xenotransplants work. Also, I think, for our audience, it's well to keep in mind that the average wait in coastal California for a kidney transplant, absent a living donor, is over 10 years. So we would likely be some of the first test cases out here in the West. Now we're moving on to the technical parts of this with Vasishta Tatapudi, who got his MD training in India, did a fellowship at UCSF close by here, and then became a transplant nephrologist at NYU Langone, where he works with Dr. Stern. He's an associate professor at the Grossman School of Medicine, and is another member of the NYU Langone xenotransplant team. You now have the floor. Vasishta.
Thank you for the introduction, Ward. What I'm going to do is pick up from where Dr. Stern left off, perhaps recap some of those things he was alluding to, because this is a complex topic. And so this is sort of a timeline of how things have evolved in xenotransplantation, which, as Dr. Stern was mentioning earlier, involves transplanting organs, tissues, or cells from an animal source into a human recipient. Some form of xenotransplantation or the other has been attempted since, I should say, the 1700s, when transfusions from animals, blood transfusions from animal source into humans was attempted, obviously not with a great deal of success. But in the early 1900s, pig and goat kidneys were transplanted onto the arm blood vessels into humans. And these organs were immediately rejected because of cross-species immunologic incompatibility. And similar transplants, for example, a chimpanzee kidney was implanted into a human female, a 23-year-old woman in New York back in 1964. And this kidney actually functioned for several months. And fast forward to around the year 2000, new technologies have emerged, cloning and gene editing with CRISPR technologies, and these have really improved our ability to engineer animal organs to more closely resemble human organs so that a rejection of these organs by our immune system becomes less likely. And so this is what has allowed us to move closer to clinical xenotransplantation, which means transplanting animal source organs into humans. And today, pigs are considered a suitable animal source for a number of reasons. One is the organ size and physiology of pig kidneys and hearts. They resemble humans quite closely. And so they would be expected to function well. Another reason pigs are considered a good animal source is because of their breeding characteristics. They achieve large litter sizes. And as Dr. Stern was mentioning earlier, the aim of xenotransplantation, if it were to become a reality, is to address the acute shortage of organs. This is a crisis of epic proportions. And as Ward was mentioning earlier, the waiting times are inordinately long in certain parts of the country. And where I trained in California, 10 years is a terribly long waiting time. Some of these patients would go on the waiting list and we would forget about them for years. And if they still happen to be alive 10 years down the road, we would call them in for transplant. But as you can imagine, a number of patients don't make it that long. Many either become too sick and are removed from the waiting list, or they die waiting for a kidney transplant. So this is the crisis that xenotransplantation aims to address. And the other reason why pigs are suitable is because they can be genetically modified. And I'll talk about why they need to be modified before using their organs for transplantation. And I think Dr. Stern mentioned that as well, but it bears repeating. And finally, obviously, there are certain ethical issues that need to be addressed before this were to become a reality. But under current ethical, the framework under which, the ethical framework of today, pigs are consumed as a source of food around the world. And also, a number of pig organs, for example, heart valves are used, pig source heart valves are used in human patients routinely. There are a number of medicinal products that are acquired from pigs as well. So at least at today, pigs are considered to be a reasonable source of organs, even from an ethical standpoint. So this is what would happen if a genetically unmodified pig kidney was implanted into a primate. And this is a picture of a pig kidney implanted into a baboon. Immediately after transplantation, the kidney looks pink. That's what you're seeing there on the left. That means it's well perfused. It's got a good blood supply and it's probably functioning for a few minutes there. And then 10 minutes later, you see that same kidney modeled, and this kidney is for all practical purposes non-functional. It's a dead kidney that needs to be removed. So this is what would happen if we didn't genetically modify these pig kidneys before transplant. And at a microscopic and a cellular level, this occurs because there are certain antibodies that all humans possess. These are known as anti-Gal antibodies, which attack certain proteins that are present on the surface of blood vessels in these pig kidneys, and then they activate a number of immune reactions that set up a cascade of events that lead to the destruction of these kidneys. And I'm putting this up there not to show complex chemical structures, but to draw attention to this molecule known as alpha-gal, which is primarily responsible for this immediate rejection. Alpha-gal is a molecule that was discovered back in the 80s, and it's a molecule that's present in bacteria and pigs, but during the course of evolution, it was lost. So apes, old world monkeys, and humans, we don't possess it. But we actually have antibodies against this particular molecule. So if you transplant a pig kidney which possesses alpha-gal into a human that has these antibodies, it's immediately rejected. And that's where genetic engineering comes in. We can now, with the use of CRISPR technology and cloning technology, genetically alter pigs so that they lack this molecule. So we knock out this molecule called alpha-gal. So in a sense, these pigs look more similar to a human. As a result, they look less foreign to the human immune system, and they don't get rejected immediately. And so, again, as I said, we use CRISPR gene editing technology, which, as many of you may have heard, is a revolutionary gene editing technology that's been, was invented about 10 years ago, and it's the subject of Nobel Prize winning, work. So using these sophisticated genetic engineering techniques, scientists have modified pigs and used their organs and tested them out in non-human primates like baboons over the last 2 decades. And progressively, the outcomes or the survival of these pig kidneys in baboons has progressively increased. But testing these organs out in non-human primates is one thing, but going to human clinical trials is a whole other ballgame. It's a giant leap. So that's where decedent xenotransplants came into the picture. And this is what Dr. Stern was talking about earlier. We took these genetically modified pig kidneys and tested them out in brain dead individuals who were kept on life support in an ICU. And what that allowed us to do was to test our surgical techniques, the function of these organs, as well as our immunosuppressive medications in a human, a setting without risks to living humans. And once we found that these pig kidneys functioned reasonably well in decedent individuals, we then moved on to testing these out in living individuals. And I won't go over too many details because Dr. Stern's already gone over some of these patients and the data that we gathered from these patients. The first 2 transplants in living humans were done in Boston and at NYU Langone in 2024. So that's just about a year ago. And then two more transplants using pig kidneys where the recipients were living humans. They were done again at NYU and in Boston. And we had the opportunity, Dr. Stern and I, to take care of 2 out of these 4 patients. Both of these patients, they certainly derived a benefit. But the stories, a lot needs to be told yet. But at the end of those 4 transplants, we gathered a lot of information, and I think we know a lot more now about how these kidneys function in living human recipients. But there's still a number of things that are of interest to me as a nephrologist and will certainly be of interest to patients who potentially will participate in clinical trials. And these are some of those things that I am interested in. Renal function, that's of primary interest. Will a pig kidney function similar to a human kidney? Will it clean the bloodstream as a human kidney would do? Will it maintain electrolytes like sodium, potassium, calcium, magnesium, all of those at a normal range? And then the other important thing to consider is, are there further genetic modifications that we need to do? Is it just alpha-gal? Is it other molecules that need to be removed or added on that would make these kidneys more compatible to a human recipient? What would the mechanism of a rejection look like in a pig kidney transplant as opposed to a human kidney transplant? That's really important, because if we understand the mechanism by which a pig kidney would be rejected, then we can develop targeted drugs to prevent those rejections. What are the optimal cross-match techniques? These are techniques that will allow us to determine who the suitable candidates are for a pig kidney transplant, and it would allow us to prevent rejection of these transplants. Preventing infections is going to be important, because it is possible that there are certain infections could be transmitted from pig kidneys into human recipients. We've not seen this so far in any of our recipients, but I think it behooves us to be extremely cautious, monitor these patients so that they don't acquire infections from the pig donor. And all of these things we'd have to learn in human clinical trials. And so, as I said, I think I'm going to dive into a few more details and show you some information we gathered from our living recipients. This is a term that some of you may be familiar with, serum creatinine. It's a measure of our kidney function, and it tells us how well a pig kidney would work. And I'm showing you data from our living recipient here who received a pig kidney. Immediately after we put the pig kidney in the top graph here, the serum creatinine comes down. It normalizes. And the GFR, which is also another measure of kidney function, again shoots up after the pig kidney is implanted in our recipient. This is the patient Dr. Stern was talking about, whose pig kidney functioned really well for about 4 months, and then she unfortunately had a rejection in the setting of an infection and possibly decreased immunosuppression. But again, this is a patient who was on dialysis for 8 years, was able to come off dialysis for about 4 months. And this is the other patient at Massachusetts General Hospital who also similarly received a pig kidney transplant, again survived for about 4 months after pig kidney transplantation. There are certain other things that we need to consider that are important to me as a nephrologist, kidney specialist. Can the pig kidney maintain water balance? Because there are certain molecules and receptors that are different between pigs and humans. We worried that a pig kidney wouldn't retain water as a normal human kidney would do. And that could lead to something known as hypernatremia, which leads to really high sodium levels, which could be life-threatening. So we tested this out in our living recipients. And what we found was a pig kidney handles water just the same way as a human kidney, very similar. And so we didn't observe hypernatremia or imbalance in sodium levels, either in our decedent transplants, which I'm showing data from here, or in our living recipient. And then another concern is, as many of you know, the heart and the kidney are the primary organs which maintain blood pressure in humans. Can a pig kidney maintain blood pressure the same way as a human kidney? Because there are molecules and hormones that a human kidney produces that that a pig kidney produces that may not interact with human molecules as hormones produced by a human kidney would. And so there were concerns emanating from non-human primate studies that these kidneys may not maintain blood pressure. But what we found was living recipients of pig kidneys maintain blood pressure just as well as allo transplant recipients or recipients of human kidneys. I'm showing you a picture here of Dr. Stern taking care of Miss Looney, who was one of those living recipients. We observed and monitored her blood pressure really closely with 24-hour blood pressure monitors, and we found that there were no episodes of low blood pressure in her case. So she did well. So some of those concerns related to whether the pig kidney would maintain blood pressure, whether it would maintain electrolyte levels. I think those concerns perhaps are overstated, but I think we need to demonstrate that in larger clinical trials as well. And that's where some of these upcoming clinical trials are going to be really important. Looking at all this data that I just described in brain dead individuals as well as living recipients, the FDA felt confident that we can now move on into clinical trials, so large trials in human recipients, as opposed to one-off trials. All of the cases that I mentioned, the 4 cases, were allowed to be done on a compassionate use basis. So we went to the FDA and said, these are patients who wouldn't survive much longer without a transplant. So would you allow us to test out a pig kidney transplant in them? And we were given one-off permission. But now the FDA, looking at all this data, has greenlit clinical trials where we are allowed to enroll several patients. One such trial that will soon get underway, where NYU will be enrolling patients and another transplant center, Johns Hopkins, will be enrolling patients in. We will initially be allowed to enroll 6 patients. The FDA is going to look at data and see how those patients do. Is it safe? Is it effective? And if it is, we will be given further permission to test this out in about 50 patients. And so this trial is about to get underway soon. And so we're on the precipice of potentially being able to offer this to patients if some of our clinical trials show success that we would hope that it would show. So that's where we are today. I want to shout out to Dr. Montgomery, who is both a mentor to me as well as Dr. Stern, who himself, as Ward mentioned, is a heart transplant recipient, and really a visionary who kickstarted this field of xenotransplantation in humans about 2 or 3 years ago, and has allowed us to now undertake these clinical trials. And of course, there's a number of individuals at NYU and other centers who are working diligently to offer this therapy to patients. We hope will benefit from this. And with that, I'm going to say thank you and perhaps take questions later on after Dr. Roy's talk is also concluded. Thank you.
Thank you so much, Dr. Tatapudi. That was really interesting, very informative. We're now going to move from one set of technical issues to another with Shuvo Roy, who's here at UCSF. He got his master's and PhD at Case Western Reserve in Ohio. He is a professor at UCSF School of Bioengineering and Therapeutic Sciences. He's been at UCSF, I believe, for more than 20 years. And he is the technical director of the Artificial Kidney Project at UCSF to build a bioartificial kidney, which will replicate the functions of a natural organ using Silicon Valley technology. Dr. Roy?
Thank you. You see my slides?
Yes.
Okay, thank you. Thank you to BAAKP, and it's a pleasure to provide this update since I gave a talk just before the pandemic and on our progress at the time and sort of plans, which were upended by the pandemic. So I'm going to talk about a different approach to providing renal replacement with a transplanted unit, but this time it's a medical device, unlike the work you've just heard, which is a xenotransplant. And we're all working towards the same goal, to provide an alternative to dialysis and overcome the shortage of organ transplants, but we're taking a different approach. And please note again that I have a disclosure about a spin-off company that hopefully at some point will be able to advance the technology beyond the university. So I approach this personally as an engineer. And what is it that we are trying to do? We are trying to mimic a device that will provide the functions of a kidney. So it's instructive to think about what a kidney does And if I'm to strip it down in terms of functions, I take a very reductionist approach. A kidney filters toxins out of your blood. That's one uh, function. And there's a host of other functions that's done, including water balance, blood pressure control, vitamin D production, etc., 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 that's done by the kidney. But in the kidney, in the native kidney, the filter, the small toxins that you have, urea, creatinine, or toxins that are about that size, are removed by the glomerulus. And I'm calling that the blood filter, hemofilter. And the rest of the functions are done by the renal, the rest of the tube, the nephron, called the renal tubule. Again, by taking a sort of a very reductionist approach, we generate in a healthy kidney about 150 liters of filtration per day. That's when your blood goes to your kidneys. But when you go to the bathroom, you're not passing out that much urine. 150 liters, about 40 gallons, right? We're passing out less than a gallon. Why? Because most of that water is reabsorbed back into the bloodstream by the rest of the nephron called the tubule. And much of that happens in the proximal tubule. And this occurs such that you have about 99% of the water being reabsorbed. So what you're trying to really mimic is this two-stage function of filtration with a hemofilter that mimics the glomerulus and something that will mimic the rest of the nephron or the tubule, which I'm calling the bioreactor. So this project started off as an engineering first project, meaning what is the desired goal? What do you want to achieve? And then try to work backwards from that. And why I say that's an engineering approach is often in medical science, we take an approach of discovery science. We try to discover stuff. And once the discoveries are made, then we say, hey, can we apply this discovery to the treatment of kidneys, cancer, heart disease, etc., etc. Here we basically came up with a list of specification or user needs, as we call them. As what we do is we want something that will provide continuous treatment. It will allow the patient to have freedom of mobility, have treatment that is more physiologic than dialysis, no through the skin connections, and thereby minimize risks of infection that come by needles or through catheters. And then, if we could pull this off, maybe avoid the need for immune suppression. And thinking about it as an engineering project, we can put sensors in and then get data, link it to the physician's office, who can monitor not only the status of the device that's implanted, but also the status of the patient. So that's how we started, was by this vision. Then some years ago, as I started talking to patient groups, including yours, the message I was hearing from a lot of the patients is, Dr. Roy and team, this is great, but remember, for many of us, we are doing so badly that we do not need you to make the perfect kidney. Let not that become the enemy of the good. And so we ended up conducting a formal patient preference study where we actually went and solicited patients across the country and some from across the world. What's important? And surprisingly to me was patients really valued the ability to be mobile and get freedom from going to a dialysis center. So much so that they would even be willing to accept a little more likelihood of death and complications as long as they didn't have to go to the dialysis center. Probably reflects the challenges of going for intermittent dialysis more than anything else. So what that told us is that we really need to focus on improving the quality of life. And to do that, you don't actually need to make the full 100% functional artificial kidney. That's the realization we came up with. What we really want is a series of specifications that get us to achieving those goals. And for a minimum viable product to use Silicon Valley terminology, the initial product, if you will, doesn't have to provide a GFR of 100%. If we can keep the patients of dialysis, if we can keep the patients to a point where maybe they're at the stage of 3 kidney disease, CKD3, they will do a lot better than they are when they get to end stage kidney failure. So by using that approach, we basically then figure out what do we have to achieve in our first generation device. So a urea clearance of about 20 to 30 milliliters per minute, not 150 liters a day, but about 40 liters per day. And then how much urine? About 2 to 3 liters, which you could replace by drinking water. And then a certain amount of, salts you must remove because of diet. And this is based on our typical diet in this country. And we figured that this has to be done by the bioreactor component, the component that will provide the electrolyte and water balance. So we've got the hemofilter mimicking the glomerulus that will provide a filtration of about 20 to 30 milliliters per minute. And the bioreactor will remove salts and also reabsorb the water such that you only need to replace water by drinking about maybe 2 to 3 liters. So this is what I call specifications, and then can we get to this goal by the tools we have at our disposal. So once we looked at this closer, we noted that given the research that was going on around the country, around the world, that there's a lot of work being done on trying to grow kidneys in a petri dish, grow kidneys in the lab. And they had made a lot of progress in different components, but nobody was perfect. So we took what I call a biohybrid architecture. We said, let us try to construct synthetically what you cannot grow precisely in the lab. So people are having a hard time growing the filter unit that is natural in the petri dish. But they want to show a lot of progress in growing the rest of the nephron, the tubule component. So I said, let's use cells for the bioreactor component. So we are taking a build, what we cannot grow in a petri dish, and grow in a petri dish what we do not know how to build via synthetic methods. And that is the hybrid approach of our bioartificial kidney. Well, interestingly, there's already somebody who had thought about this strategy before. Almost 20 years ago, there's a nephrologist at the University of Michigan who was treating patients in the ICU who had had kidney failure and associated with sepsis. And most of these patients were very likely to die, despite intensive dialysis therapy in the ICU. So Dr. Humes here hypothesized that just removing toxins using dialysis was not good enough. Can we actually provide more function than regular dialysis? So he took conventional off-the-shelf technologies, dialysis cartridges, connected them in the same architecture as our native kidneys, such that you have first a filter and then the bioreactor. And in the bioreactor, he lined it up with cadaver kidney cells. And through a series of animal studies and then ultimately human study, he was able to show that this contraption, as you see on the screen, and basically combining the filtration coupled with kidney cells in the bioreactor, he was able to show that these patients not only survived much better than intensive dialysis, but they actually produced urine. So this work was very exciting because it actually showed for the first time that by connecting a mechanical device for filtration with cells for some of the other functions of a tubule, you could actually replicate those key features of a kidney. Now, this is clearly very complicated looking, and it is complicated in structure, and it is done in the ICU unit. So as engineers, my team and my colleagues said, can we do something to move this from what you see on the left to what can be an implanted device that will provide continuous therapy on the right? And that's what has become called the Kidney Project over the years. So I'm going to take you through some of the engineering steps of how we are moving this forward and where we are today. So how do we go from here on the left to here? How do we miniaturize? Well, we look to Silicon Valley, and that's one of the reasons I moved out here, was can we take advantage of the infrastructure in semiconductor manufacturing? Silicon wafers that allows us to today talk to each other as we in this webinar. Your cell phones, your TVs. We choose silicon wafers to create features that are much, much tiny. So think about the computers out of the 1970s to the computers today. The iPhone, as you've heard, has more computing power than whatever went into the moon, you know, 4 decades ago. And that's all enabled by semiconductor nanotechnology. So we decided that let us try to bring the toolkit to the miniaturization of a renal replacement device. And the fundamental epiphany we had was let's make a better filter unit. And what you're seeing here is a photograph of a silicon wafer and the center scanning electron micrographs of our filter. These filters have a very high selectivity, means they discriminate between good molecules and bad molecules, toxins versus non-toxins. They have a very low fluidic resistance, means that they do not need a lot of energy to filter. In fact, they are such a low resistance that just the pressure difference between the artery and the vein is enough to drive filtration. So you do not need a battery. You do not need electrical power. Just the blood pressure itself is enough to operate the device. And not only that, you are able to make this using a manufacturable technology of semiconductors. And so if you look at this is a cross section of a wafer and a polymer membrane. So the polysulfone is a standard hollow fiber dialysis membrane that Dr. Humes in Michigan used 20 years ago. It's also still pretty much the same as it is today. And you can see it's about 70 times bigger or thicker than our membrane, which is to the right. Think about this. Basically means it's so thin, 70 times thinner. So for the same amount of pressure, you get 70 times more filtrate, or for the same area, for the same pressure, you could also use a lot smaller surface area. And not only that, but you can see that our membranes have what they call a very sharp cutoff, and they basically mimic the kidney's glomerulus. So we have a membrane that does not require pumps, very compact, and provides clearance that mimics the kidney without losing albumin. Not only that, we also looked at how do these membranes act as for the passage of different biological molecules. So we took an experiment that one of my students did, took a heavy concentration of different molecules you have in the body. Some of them are called cytokines, glucose, insulin, albumin, and then exposed them across the membrane and looked at what happened over the course of 6 hours. And this is a 3 or 4x of what you have in the body. And you basically saw that, first of all, no albumin went through. You did not actually leak albumin, which is something you don't want to do. As you know, if you leak albumin in urine, it's a bad thing. Second, glucose and insulin just pass through. So all small molecules, oxygen passes through, and cytokines are impeded from passing through. So in principle, you have something like this. It allows you to think about at least minimizing and maybe even eliminating at some point the need for immunosuppression. So by tuning the membrane, it becomes attractive that maybe we can get to a point where you do not need immune suppression. We also then ended up working on these membranes to make them biologically compatible, because if you put a foreign material in blood, you're likely to cause clots. And if you cause clots, well, that's a bad thing. So what you do is often you try to put blood thinners. Well, if you have blood thinners, that can lead to increased risks of bleeding. Increased risks of bleedings have its own complications. So we decided to come up with coatings that you can apply on these membranes such that there's no absorption of proteins that can lead to a thrombus, lead to a blood clot. And what you're seeing here is this one particular coating, PSBMA, basically does not allow any absorption of these proteins. And you can see the scanning electron micrographs to the right. So it allows us to think we have a strategy to eliminate, certainly minimize the amount of any type of blood thinners one may want. And some of you who are familiar with stent technologies know that blood thinners have advantages, but also significant disadvantages. So our approach is no immunosuppression and no blood thinners, if we can help it. Well, where do we get the cells? So we actually worked with the colleagues over at the University of Michigan to think about can we use their cells? Well, they're able to get their cells from human cadavers, from kidneys that could not be transplanted. So they're able to take a biopsy from those kidneys, or if the kidney was completely unusable, they would basically recover all the cells they could from those kidneys, and they developed protocols to expand the cells, meaning grow them in culture so that they could be used. And over the years, they have perfected this technique as such that depending on the donor, and this is what this graph shows here, different donors have different capacities. Younger, healthier donors have more robust cells than, say, those that are older and maybe cancer patients, smokers, etc. But we have a way to get kidney cells for our device from human cadavers. And of course, if other sources, stem cell sources, work out, we can certainly use those. If another source is obviously pig kidney cells, if that is allowed by the FDA, we would certainly import those kinds of cells into our device. But I think for now, we decided to stick with human cadaver cells. So we're here showing that we can actually grow these cells on our membrane, keep them alive. And what we decided to do a few years ago is let's take the knowledge we have and go back and test our original hypothesis. Does this actually work as the way we thought it should? So we basically built a small scale prototype that combines the filter unit and the cell unit. This is about the size of 2 decks of cards. It is not enough to provide a dialysis patient with enough capacity to survive, but the idea was, does it actually generate urine? Does it work? Does it not require immunosuppression? So we actually ended up doing this work, and what you're seeing is pictures from the very first surgery. We put this into a pig, and the blood vessel is connected to the blood vessels, like very much like a kidney transplant would. And then over here, blood's flowing through the device, here on the top left. And the purple line goes to the bladder. And we left this in, and we're able to show that at the end of the 3 days, this is our study, that we're actually creating clear fluid that was going into the bladder. This fluid had no albumin and had all the hallmarks of what you'd measure in urine. Now, again, this is a very small scale device, but what we wanted to show is it actually worked with no immune suppression, so there's no acute rejection as you saw in they illustrated in the previous presentations. We got a very small amount of urine come out, but what is really interesting for us is the ratio of urine production to what the glomerulus does is exactly in the same range as what a native kidney does. And the cells were viable, meaning they are alive inside the pig despite no immunosuppression. So this is our step at showing that there's a proof of concept that we can actually build a hybrid device that works without immune suppression and did not require anticoagulation, no need for blood thinners, and was functional in the same way that you have in normal physiology in a human. So how do we move forward? But we have to scale our devices up for clinical capacity. We are producing microliters. We need to produce milliliters per minute of urine. Once we have been able to scale up to the size that we need, which means we need to put more surface area of silicon filter, more kidney cells, then we can go to the FDA and ask for approval for the first in human testing. To get this moving forward, we also have to recruit partners to help us get into manufacturing and then ultimately distribute to patients. That is the path we must take. But what are the barriers? The barriers is each of these steps, getting there has a number of technology barriers, what I call prototype development and testing. It's really about scaling up. We have to think about how the FDA will allow us to move forward in a manner that is acceptable to them, but doesn't slow us down. Second, we have to think about who's going to pay for this, who are going to be the manufacturing distribution. And then we have to educate patients like you and your clinical caregivers about the potential here. So we need your help. We're nowhere close to the end of the project. We have shown that it is possible to do what we said we would do, but we need to move this forward. And one of the places we need your help is really doing something, which is to tell your physician we want to have them fill out a survey for us, because we're trying to understand, very much like we understood what patients want, we want to understand what physicians would consider important for them to prescribe a device like this for you. So you can send them this link, or you can take a picture of the QR code and send that out, and that will allow them to then fill out the survey. So anyway, thank you very much. Again, I could also mention a number of my funding supporters, but also point out my nephrology colleague who's now at the University of Michigan, who has been my clinical partner for the last 15 years or so. So thank you very much. Appreciate it.
Thank you, Shuvo. And we will turn on to some questions as we approach the end of our 90 minutes. And I'll start with ones that appear to me to apply to both technologies, both the xenotransplantation and the artificial kidney. The first one will be, who can qualify, and including in that is, will there be priority for people who have been told that they're too old to get a normal transplant? Jeff or Vasishta, would you like to start?
Well, I'll at least comment on part of that is a lot of programs in the country have age requirements, and then there are a lot of other programs in the country that don't have those age requirements. And not to necessarily highlight NYU, but we look much more at the person. If you're a very functional 75-year-old, or even a very functional 80-year-old, I think we look much more at that. So I think if you're being told that you're not a candidate because you were 69, 3 days ago, and now you're 70, I would suggest looking for a different program if you're able to geographically look at a different place. That being said, the criteria for the first clinical trial, the United Therapeutics trial, is for patients between the ages of 55 and 70. That unfortunately is a hard restriction for clinical trials from the FDA perspective. Vasishta, do you have other comments on that?
Yeah, no, I think just maybe perhaps to elaborate on what you were saying earlier. We at our institution don't draw a line based on age for an allo transplant, which is a human to a human kidney transplant. So I think there's 80-year-olds and then there's 80-year-olds. You could have a healthy person at the age of 80. You could have someone who's in their 40s, but not quite a good kidney transplant candidate. So I think for the purpose of thinking about a regular allo transplant, you should explore, several centers if that's possible, and choose the center that perhaps accepts, is more flexible in terms of age cutoffs. But for the purpose of the upcoming xenotransplant trials, at least the first iteration of the trial that we at NYU are going to be undertaking, there are certain age restrictions for patients that we will enroll. That's between the ages of 55 and 70. But this is just the beginning. I suspect, depending on how these trials succeed, the next iteration might perhaps relax some of those age restrictions. I think that's certainly going to evolve.
Yeah, I should point out, I was 74 when I had my transplant, and at that time it was listed at not just NYU, but also several other transplant centers. Shuvo?
I think my physician colleagues have answered it very well. I mean, I think the important thing is they have to be they have to be healthy enough to withstand surgery. I think simplistically, as an engineer, that's maybe the way I answer that question. If they can't withstand surgery, they're probably not a candidate for what we're going to do.
Another question is whether this came up from several different people. Will Medicare and Medicare supplement insurance pay for the surgery after Vinitz after visits, excuse me, labs, drugs? You see any questions there?
I think obviously the answer is I hope so. Right? Dialysis is expensive, and actually in the long run, kidney transplantation is cheaper. And so I hope that, as we realize the day when the organ itself is not the majority cost and that it's really just maintenance care, that all becomes cheaper than dialysis. And so I'd hope that sort of everyone realizes that, including insurance companies. Currently, that's not the case. I mean, there's no payment for any of these things in the experimental phase.
Right.
Yeah, I just want to say that, we've had some discussions with CMS, and the feeling is, once you, again, not just us, but all the work that's being done in innovative kidney replacement technologies, if there is evidence that this will actually, improve the outcomes and save costs, they would be very supportive. So I think they understand the financial challenge as well as the burden on patients. So I'm optimistic that it'll get covered.
And then third, renal carcinoma, would such patients be eligible? Currently, they're not eligible, as I understand it, until they've been cleared for 3 to 5 years, depending on the transplant center.
Yeah, I'll say, I think the question perhaps is asking about the eligibility of patients who have renal cell carcinoma for an allotransplant, for a human-to-human kidney transplant. If that's the question, the answer is it depends on the size of the tumor, the spread of the tumor. Certainly, if the tumors are small and they haven't spread, and if the kidney can be removed, um, uh, um, it's quite possible that there is no tumor-free wait time. Essentially, meaning you could proceed to transplant once the kidney with the tumor is removed. Of course, if the tumor is larger, some of those time restrictions, 3 to 5 years, may apply, but it really depends on the size of the tumor. But I think to just fast forward that a little bit and to talk about whether you would be a candidate for a xenotransplant if you have a renal cell carcinoma. Right now, again, I think there's, the details matter, but again, it depends on the size of the tumor and, a history of a renal cell carcinoma wouldn't necessarily exclude you from a xenotransplant trial, but I think we would want to see a certain period of tumor-free waiting time before we allow those patients to get transplanted. And I don't want to, off the top of my head, I think we would want to be waiting for about 2 years for a patient with renal cell carcinoma to be tumor-free before we allow them to be transplanted.
This flip side of the other question, will younger patients be eligible for the clinical trials when they have, in the case of xenotransplant, and starting now and later on for the case of the artificial kidneys?
If you want to take that.
Yeah, I mean, I think so. Currently, no, by the strict definition of the trials, and I think that there's a lot of maybe paternalism from the FDA in the definition of the patients that they want to undertake the first clinical trials. And I think we probably all have a little paternalism. We don't want to hurt someone young with something that may impact their future ability to have a human transplant or other. That being said, I think young patients with end-stage renal disease and chronic kidney failure are certainly robust enough, generally speaking, to be able to tolerate a xenotransplant and may be great candidates down the road. Currently not candidates in the trial setup, but I think in the future, I think the age expansion will occur.
Shuvo?
Yeah, so we've had a chance to talk with the pediatric group at the FDA, and I think there's a sea change in how they're approaching innovation. So in the past, they would wait, I guess I should say the global they uh, would wait for something to go to adults and then go to patients because there was this feeling like we do not want to endanger patients who are very young, pediatric patients first. But I think there's a recognition that patients are not necessarily, they're patients that may not be able to wait until we get all the data from the adult population that's necessary. So there's actually some thinking now about how can we, for the right patient, have an approach to get to pediatric populations quicker. So I think by the time we get to that stage, there will probably be some changes in how they might approach it. But for now, it's usually let's first do it in adults before we go to children. But because of the FDA's own initiatives, there's an interest in putting pediatric patients first, and so there may be different guidelines in the next few years.
Are applications for the clinical trials for either of these techniques open now?
Yeah, the United Therapeutics xenotransplant trial, you can go to it on clinicaltrials.gov. We can probably provide the link for that if I can find it somewhere. And then certainly you can contact our institution, if you're interested in it as well.
Yeah, for the artificial kidney, we do not have a clinical trials approved, so we don't have any list. What we do have is an interest list for people that want to be aware of what the status of our technology. So if you go to kidney.ucsf.edu, I'll put it in the chat. You can go and play one place and you can either sign up and we'll keep your name and put you on through all our newsletters and social media so you're up to date. And we call that a clinical trials interest list, but we're not at a point of recruiting now.
Okay, I think those are the sort of the common questions. The several for the xenotransplant team. Have you found any serious problems for patients who did trial implants and then had to go back to dialysis?
Yeah, so our most recent patient who received a xenotransplant, as I was mentioning earlier, had immediate graft function in the sense that she was able to come off of dialysis and that kidney worked well for about 4 months. And then unfortunately, she had a rejection, but she was able to return to dialysis. So she's alive and healthy, back on dialysis, obviously not the outcome she had hoped for, but a failed xenotransplant is not a death sentence. And there's always the fallback option of dialysis. Obviously, this is surgical intervention, and these patients are placed on immunosuppressive medications for as long as these pig kidneys work. And that might take a toll on patients, but our effort is to minimize the toll that the surgery and the immunosuppression takes. And even in the event that the kidney fails, we want to be able to preserve their ability to go back onto dialysis. And as we make improvements in immunosuppression and our surgical techniques and survival of a xenotransplant improves, that thought or the time frame might be much longer, right? I mean, even with an allo transplant, a human-to-human kidney transplant, these kidneys have a certain shelf life, and after a certain period of time, when a human kidney fails, they go back on dialysis. I think as time progresses and these trials educate us, we would hope that the longevity of these pig kidney transplants increases as well.
How many people will be part of the clinical trial, and what is the anticipated length of the trials?
So the first set of the trial is as Dr. Tatapudi mentioned, about 6 patients. It starts off with 2 patients, and we see how those progress, and there's a waiting period, and then subsequent transplants after that at multiple sites across the country. And then there's a pause at that point then for FDA review before the expansion to about 50 patients is what I think the stated goal is. That comes in sort of early outcomes and late outcomes. So we look at, I think, essentially 6-month outcomes of the transplants early on, and then how well they do after that. So the endpoints of the trial are actually somewhat ill-defined because we want to see how patients do in lots of different categories.
Okay. Couple of I guess practical questions. How long will it take for the kidney to wake up, the pig kidney to wake up? And if the kidney fails, will it be removed or left in the body?
I can take that one. So almost immediately, just like a living donor transplant, for almost all of the kidneys that we've implanted thus far, within about a minute or so after the reconnection of the blood vessels, the kidney starts making robust urine. And it really depends on the clinical scenario at which the kidney failure occurs of a xenotransplant on whether we would leave it in or take it out. We've obviously taken out all of the ones to date for various different reasons, and often it's to allow full withdrawal of immunosuppression at that point to prevent any further complications of the immunosuppression. So we generally will take them out, but there are certainly scenarios I think that can be envisioned where the kidney would be left in if it was risky to undergo a surgical procedure.
If can a recipient of a xenotransplant have it done a second time or a third time?
We don't totally know the answer to that. We suspect the answer to that is yes, in the same way that human kidneys can be done. It is possible, again, depending on sort of the scenario and why a kidney was lost. Does the body develop sensitization? Do you create antibodies against pig kidneys very strongly, the same way that you might against a human kidney that you rejected? In which case that would preclude or make really difficult to undergo a second xenotransplant. But the thought is that if you do not become sensitized, that you could actually repeat it several times.
If I could add one more thing to that, I think very often the question that comes up is what happens to my position on the waiting list for a regular allotransplant if I get a xenotransplant and then that fails? The answer is xenotransplant doesn't alter your position on the kidney transplant waiting list. I suspect if you get a xenotransplant and that transplant's working, you would be inactive on the waiting list for a deceased donor transplant, a human transplant. But should the xenotransplant fail, you could still retain your position on the waiting list.
Okay. And
from that regard, I'll chime in a little bit, is that none of our data to date show that having gone through the xenotransplantation process, do you make more human antibodies or anything like that. So we don't think that it tangibly harms you from having a pig kidney implanted by that point.
do you guys know the ages of the first 6 people for the trials?
It will be in that range, 55 to 70 for
Okay.
the first group.
And finally, another practical question: where are the pigs raised, and what's their diet? If you know.
I don't know exactly what they eat. There are certainly I think there was a CNN documentary about the pigs and stuff, and you can watch some videos about it. It was quite interesting. But they are, so I don't know specifically the diet of what they are, but it is in Middle Eastern America.
Okay, I think that's all the questions I had for the NYU gentleman. And now for Shuvo. Will the artificial kidney resolve proteinuria issues, which aren't resolved by dialysis?
That's correct. So our membranes are designed to discriminate such that you avoid the need for losing protein. So in dialysis membranes, there are ways of trying to avoid proteinuria by trying to work with the dialysis, but you also lose other things in the process. But all the tests we've done so far, and admittedly our test, the longest we've done, the filter test is up to 30 days. We've been able to show no loss of protein, no loss of albumin-like proteins anyway.
Will there be any limitations on lifestyle or diet for the recipients of artificial kidneys?
It's always hard to say. Like it's been said, it's hard to predict the future. But I think if you look at what we are proposing as a minimum viable product, we're not proposing 100% kidney. So I think the two functions that you will achieve with the device is continuous removal of toxins and water balance. But I think you'll still need medications to maintain the other functions like they do today with dialysis patients. You may not need immunosuppression or need very little immunosuppression, but you'll likely need some ability to make EPO. So you'll still need some medications. And in a first generation device, when you strip it down, I think we're not focusing on beyond the filtration and water balance. But eventually you could think of integrating cells that produce EPO, produce other, and help with maybe more sophisticated functions of the kidney with blood pressure regulation.
Will there be any issues with deterioration of the device or the parts of the device, the filters, for example? Will there be any upkeep required?
Yeah, it's a great question. And of course, any artificial system is likely to degrade, fail, and I think we have to think about alternatives or how you mitigate the chances. So I think the approach you're taking is learning from our colleagues who do vascular surgery with, for example, grafts, people who do work with ventricular assist devices, artificial hearts, where they actually have to be prepared that there may be failures. So I think the idea is, yes, the devices may fail. We're hoping that we get a lifetime of more than 5 years, maybe 10 years. It's hard to say this without actually doing all the real world tests. But interestingly, that was one of the reasons we did our patient preference survey, because I'd get that question from many people, how I want this to survive and how long will it survive? So we flipped it and said to the patients, what would be an acceptable time for a maintenance procedure if we could get you off dialysis? Interestingly, the answer is 1 to 2 years, which told us that, if you can get the device to work for at least, say, 2 years, patients would be willing to come in for some sort of periodic maintenance surgery. But our goal, I think, is like a pacemaker, 7, 8 years. I think that's reasonable to at least think about.
Okay. And once the device becomes commercially available, maybe you answered this in your remarks, I didn't notice it. What will be the cost versus the cost of a human kidney transplant?
So for everybody out there, I think what is the cost and what does it take to make it are two different things. Okay.
Right.
So what it will be sold for is very much dependent on reimbursement and the capitalistic system. I mean, that's frankly what it comes down to. Medical device manufacturers are trying to recoup costs, so they'll try to jack up the prices. What we can do is to compare, what's the cost of a transplant, regular transplant today, and what the cost of goods we have, and there's a big difference. So I think it will be no more than a regular human transplant, potentially a lot less once we have the economy of scale.
That's all the questions that were really focused on the artificial transplant, but a few others have come in for the Xeno team. If positive for BK viremia, could you get a xenotransplant?
I think that's a great question. I think we would, initially, at least for the clinical trials, want a BK viremia to become undetectable before a pig to human kidney transplant, as would be the case for an allotransplant. I think the question of BK viremia only arises if you have already undergone a transplant. And I'm
Right.
assuming the question is if you've undergone a kidney transplant that's possibly on the verge of failing because of BK virus, and you still have virus, will you then be a candidate for a xenotransplant? I suspect the answer would be yes, because if your kidney is failing, if you would stop your immunosuppression, allow the BK virus to become undetectable, and then you could undergo a xenotransplant. I think that would be the pathway for someone with BK viremia to get a xenotransplant. But I think it's a very nuanced question. We do not know if a BK virus would cause the same problems it would cause in a human kidney. Would it cause the same problems in a pig kidney? That's unknown. And in fact, to the best of my knowledge, a pig kidney, pigs don't, have a BK virus infection. This is a BK virus is unique to humans, as far as I know. So, it may not be a problem for a xenotransplant, but something we still need to understand better.
Is dialysis harmful in the long run? And if so, is xenotransplantation an intermittent reprieve?
Sounds like a nephrology question, so I'll take that. Dialysis itself isn't harmful. And as a nephrologist, I have to say that dialysis is actually life-saving. The problem is it doesn't completely take over all the functions that a normal kidney would do for you. For example, doesn't produce certain hormones, and also it's not a 24/7 situation with dialysis. Most patients who are on dialysis understand that it's only done for about a few hours a day, maybe 3 or 4 times a week, whereas a normal kidney or a transplant kidney functions 24/7. So it's not a completely physiologic solution. But yes, the answer is a xenotransplant can allow patients to come off of dialysis. At this point in time, it looks like these transplants have a limited survival, but our hope is to prolong that survival. And I think, as Dr. Roy was mentioning his survey results earlier on, I think they kind of inform us as well. Patients are happy if they're able to come off of dialysis for 1 to 2 years. And right now, we're at a stage perhaps where a xenotransplant can give that reprieve to patients on dialysis. Maybe 6 months, maybe 1 year. Our hope is that in the long run, that survival advantage is much longer.
Thank you. For a pig donor, are both kidneys removed, or is one left for the pig to live on?
But both kidneys are taken from the pig donor, and then the pig is sacrificed afterwards, and that's for various different reasons. Also, namely that actually their U.S. has requirements that major surgeries on animals can only occur essentially once, for lots of different reasons. Yeah, it's a terminal surgery for the pig donor, and both kidneys are taken, and that's on the recipient side. If there's a technical reason or technical complication with the implantation of the first kidney, we'd actually proceed sort of directly with the second. And so it's sort of our emergency reserve. Lots of things can be different when you're not at the mercy of an organ donor pool that's limited, right? When you don't have a scarce supply, you can do things like have an emergency backup in the operating room, that sort of thing.
Question for Shuvo, who is currently funding the kidney project?
Yeah. So just for everybody, I know while the questions coming, I answered some of these also online just so that we save time. But we have relied mostly on grants and donations. The question that comes to me is why don't you have more investors or companies supporting what we do? And frankly, the state of the economy and the state of the VC world is such that for kidney technology, they would like to see us in first in human studies before that would be considered. So right for now, it's based on grants and philanthropy advancing our work.
And one last question, also for Shuvo. Will the artificial kidney help reduce or in some way address diabetes?
Well, I think, in fact, I may actually have to think about this in collaboration with my nephrology colleagues. So if you have a device that's providing better removal of toxins as well as sugar, you might say that that may help with controlling diabetes. Although I have to say, from a clinical perspective, I can't really answer that. Maybe Dr. Tatapudi could weigh in.
Yeah, I think if, based on what I understand of Dr. Roy's technology, I mean, ultimately, diabetes is a disease of the pancreas, and then there's insulin resistance. I can't imagine that replacing a kidney, just like if you do a kidney transplant, you're still left with diabetes if you have diabetes. I suspect, an artificial kidney will not cure diabetes, but I think it certainly will replace kidney function, and that's a good thing. So.
Okay, we run over a few minutes. I apologize to the attendees for that, but there were a lot of questions, and there's still a few on the line that I didn't ask because I think they were addressed for the most part in the presentations. Thank you all very much. And we look forward to getting an update maybe in a year or two.
Thank you.
Thanks, Jorge.
Deborah?
Thank you, everybody, for attending. Thank you, speakers. This has been absolutely fascinating. So thank you very much. Our next kidney support group is Sunday, August 10th. The recording of this will be online sometime in the next couple of days. And I think, and we're attending a health fair in Oakland. The information is on our website. So please visit our website at baakp.org, and we have videos of past presentations. We'll have PowerPoints from this and this recording. So thank you all. Thank you, speakers, so much. And Ward, great webinar. So bye.